Okay students, welcome to another video of short circuit analysis chapter. In the previous video we discussed about the asymmetrical fault analysis, and we discussed that in order to carry out asymmetrical fault analysis we need to convert our unbalanced system into a balanced system. We use Fortescue theorem to convert the currents and voltages into positive, negative and zero sequence values, and then we also discussed that what is the significance or what are the electrical characteristics of sequence current, in which we discussed that if we have a zero sequence current, then this cannot flow through the system unless we have a fourth path. That is, we say that a neutral path is required for flow of zero sequence current through the system. In this video we will be studying sequence networks. Now we already know that there are three currents and voltages present in the system, like positive, negative and zero sequence values. So basically sequence network focuses on drawing separate networks for the positive sequence, negative sequence and zero sequence, because we have already discussed that if the system is ungrounded, there is no neutral, or if there is a delta connection, right, then the zero sequence current will not be flowing. However, the positive and negative sequence current will still be flowing because it doesn't need a fourth conductor to flow, right? So it is recommended to draw the network in terms of positive, negative and zero sequence. Whichever current is not flowing, we can open it, we can mark it as open circuit, right? So in this video we will be discussing the sequence networks for three components. The first one is impedance loads, right? And in the later part we will be discussing the sequence component for transformers and then for generators. So whenever we are talking about impedance loads, let's start by considering a Y connected load. So let's consider a Y connected load where the neutral is grounded with an impedance of Z and Z, right? Y connected load, and here our neutral is grounded by an impedance of Zn, and Zy is the phase impedance for each branch. This is phase A, B. At the moment we are considering a balance. Now if we consider the line to ground voltage, this is the voltage between line A to ground. So we can say that this voltage VAG is equals the sum of VAN, that is from A to N, the neutral point, plus the voltage at the neutral line. And VAN, as per the Ohm's law, we know is equals to the product of IA times Zy plus IN times Zn, and In in itself is equals to what? The phasor sum of all the three currents, IA plus IB plus IC times Z of n, right? Or in other words, we can write, rearrange it, IA Zy plus Cn plus IB times Zn plus IC times Cn, right? Similarly, VB to ground will be equals to IA times Zn plus IB times Zn plus Zy plus IC times of Cn, and VC to ground will be equal to IA times Zn plus IB times Cn plus IC times Zn plus Zy, right? So we can write it in the matrix form as VA to ground, VB to ground, VC to ground equals the diagonal elements are Zy plus Zn then the non-diagonal elements are all Zn. Again, this is a symmetric matrix times the currents are IA, IB and IC, right? We can also simplify this or by just writing VP, that is V phase, equals ZP, that is the impedance matrix per phase times of I. And now we know that we can convert the phase voltages into the sequence components as well as the phase currents into the sequence component by the using the symmetrical component transformation matrix. So VP is equals to AVS, so this would be AVS equals ZP times AIS, right? And when we multiply with A inverse AVS is equals to A inverse ZP AIS. So here A inverse A would be equal to I, and I times of Vs will be Vs. But A inverse ZP, since we know that the matrix multiplication is non-commutative, so it will not be equal to I, and we are just referring it as Zs, that is the sequence matrix for impedance, the sequence component for impedance, where Zs will not be equal to the unit matrix, rather it is equals to A inverse times Z times of A, right? So when we just solve this, we will get Zs equals A inverse is 1 over 3 1 1 1 1 A square 1 A square A. Then we have this Zy plus Zn, Zy, sorry, Zn, Zy plus Zn, 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 Zy plus Zn equals this would be now A 1 1 1 1 A square A 1 A square. Then we carry out the multiplication. Again, we will not be going into the details of multiplication. The answer that we get is zy plus zn plus a square zn, and we know that a square solving and using the property 1 plus a square equals to 0, the simplified version that we get for zs is that it is equals to zy plus 3zn 0 0 0 zy 0 0 0 0. Now, which is another proof that what is this zs? This is equals to z0, z1 and z2, right? Now you can see clearly that the neutral impedance is only getting involved as 3 times, and for the value of 0 sequence only. It will not be there for the positive sequence or the negative sequence. Clear? So now our equation will become V0, V1, V2 is equals to Zs, which is Zy plus 3Zn 0, 0, 0, Cy 0, 0, 0, Zy I0, I1 and I2. So when we multiply it, this is from the previous slide here, as we saw that Vs equals to Gs times Is. We have just put the value of Zs in this equation 1. And now we can see V0 equals I0 times Zy plus 3Cn. V1 equals I1 times Zy, and V2 equals I2 times of Cy. And this is what we call that we have 3 impedances, positive, negative and 0 sequence impedances, for which the equivalent circuit is. Now let's draw it. First we have the 0 sequence, right? Zy plus 3Zn. Direct addition represents what? A series combination of Zy and 3Zn. This is Zy, this is 3Zn. This would be the voltage V0 and the current I0 flowing. This is 0 sequence, right? Next, positive sequence, just a single impedance, Z1 equals to Zy. The current flowing is I1 and the voltage across it is V1, and same is the scenario for 0 sequence. V2 equals to Zy I2. Clear? So this was all for the impedance. So the impedance sequence network for a Y connected impedance is that we have 0 sequence flowing, we have positive sequence as well, and we have a negative sequence as well. If we have a delta connected impedance, then this neutral impedance is what? Infinite. There is no neutral, which means this is open circuit, there will be no 0 sequence current. No 0 sequence current in the delta system. Positive and negative, yes, they will exist. For delta connected impedance, we only have the positive and negative sequence networks. The 0 sequence network is open circuited. Why? Because there is no neutral impedance. I hope it is clear. Okay, now next let's discuss the sequence networks for impedance loads, right? The sequence networks for transformers. Sorry, we are done with the impedance loads. Now we are considering the sequence network for transformers. Now here we need to be a bit attentive. We know what is the equivalent circuit of a transformer. The equivalent circuit of a transformer is fairly simple. I am talking about the simplified version, so it is like this. This is the equivalent impedance, and this is the primary side, and this is the secondary side, and we refer it on either side, right? So this is Vp and this is Vs. We refer them to either side. This is Ip and Is, and when we include the turns ratio, it either gets A square or divided by A square, right? Now the question is the zero sequence network, the positive and negative sequence network is same irrespective of the connection time. That is, the positive as well as negative sequence impedances or sequence network will be the same. Let's consider that any transformer item, right? The positive and negative sequence network will be like this. This one is Z1 or equals to 0. This is positive as well as the negative sequence. Both networks will be the same with voltages and the currents, right? This is positive and negative sequence network, and then we have zero sequence network. Now the zero sequence network, as we already discussed, depends upon the transformer type, depends upon the type of connection in the system, and we can have multiple types of transformers, right? The simplest of which is let's consider a Y transformer in primary and a Y in secondary as well, right, with both windings grounded. Now since the primary as well as the secondary, both windings are grounded, so this means that there will be a zero sequence component existing, or in other words we can say that a zero sequence I1 or I2 current will be flowing through this transformer, right, with a sequence impedance of Z0 is equals to 3 times of Zn. Clear? Now comes the trickier part, part B. Let's say I have a transformer where the primary winding in Y and grounded and the secondary winding is in Y, but there is no neutral grounding. Now what will happen when we discuss this? The positive and negative sequence components will be the same, no issue, right? But talking about the zero sequence component, primary side is grounded. This means zero sequence current can flow, but the secondary side neutral is left open circuited, and we know that the transformer works on the MMF balance. Primary side MMF must be equal to the secondary side MMF, and since there is no path for flow of zero sequence current on the secondary side, the overall circuit will be open circuited. We are saying okay, fine, that current can flow on the primary side, but on the secondary side it is open, so overall there will be no zero sequence current flowing in the circuit. I am repeating it again. The primary side is neutral, grounded. Okay, you can say that current can flow through here, but transformer works on the balance. Any current that flows through the primary creates a flux and has an impact on the secondary. And since secondary winding cannot carry zero sequence current, therefore there will be no zero sequence current in the primary winding as well. This one is the sum of primary and secondary. So primary is here, but secondary is open, so the current will not be. So got it? Now the third one is again simple. Here the primary is ungrounded by and the secondary is grounded, and as you know that in this scenario the behavior will be same, that primary will be open circuited, there will be an impedance, and due to the transformer MMF balance principle the current will not be flowing. There will be no zero sequence current if the transformer connection is of this method. And same will be the scenario if the transformer is primary delta, secondary Y ungrounded, or primary Y ungrounded with secondary delta. This scenario will be same. Okay. The only difference is that it will be open circuited from both the ends. We can draw it like this. Right, but still there will be no zero sequence current. Or let's draw it separately. We can draw it separately. Now comes the important scenario. Okay, first let's draw these ones. Delta Y ungrounded, positive, negative, same. Open. I will be explaining it in a while. And E is Y ungrounded with delta. This would be open. You people might be confused here, but I will be explaining it in just a bit. Now let's look at a different type slightly. This is the scenario with delta Y ground. Now the positive and negative sequence network will remain the same. Talking about the zero sequence. Y side, since it's grounded, it will be supporting the flow of zero sequence current, I naught. What about the delta side? This side. Delta lines cannot carry the zero sequence current, but there can be a flowing zero sequence current within the delta windings. It will not go into the lines. I am repeating it. That delta winding can have a circulating zero sequence current within the delta. This current cannot flow into the lines. But if there is a current circulating within the delta, this means that the balance will be maintained, and therefore we say that zero sequence current can flow at the secondary side but cannot flow at the primary side. Why? Because the delta lines cannot carry this zero sequence current. But delta winding can carry circulating current to balance this secondary zero sequence current. Got it? Similarly, if I have a Y grounded, this was F, this is G. Y grounded delta connection. Now it will further clarify your point. Positive negative is the same. The primary winding, yes, it can carry zero sequence current. What about the secondary winding? No, open circuit. But there can be circulating current within this delta connection just to balance the current from the primary side, as we discussed that the transformer works on MMFL. And if it is so, this means that the current can flow on the primary side but not on the secondary side of this transformer. I hope that it is clear now. This was the trickier part. And now coming back to these two, which I said that we will be discussing after the E, F and G. So D and E, delta and Y. Delta can not offer this value, so this transformer is again open circuited, and since this is open circuited, even if you draw this or not draw this, it's the same. This means there will be no zero sequence. Okay, draw it or no, don't draw it. Ultimately this is a series circuit, open circuit, so there will be no impact, right? So to summarize, we need to check the transformer. If the transformer is ungrounded, there is no provision for zero sequence current on the in the lines as well as within the winding, so there will be no zero sequence current on either the primary side or the secondary side. If the transformer is grounded, then the connection or the flow of zero sequence current depends upon the other side of the transformer. Primary is grounded, secondary is Y ungrounded. No current, why? Due to balance. Primary is ungrounded, secondary is grounded, no current due to the MMF balance. If primary is delta, secondary is grounded, current can flow through the secondary because delta will be equal to balance within the by the circulating current. Same is the case for primary grounded, secondary grounded. I hope it is clear. Now the last sequence network that we need to discuss here, and you people will of course be wondering why are we discussing these networks. So let me clear that in the next video of unbalanced or asymmetrical fault analysis, we will be using these symmetrical networks, sequence networks. That is why we are studying it. The last one is for loaded generators. Right? So now let's consider a generating system, three-phase synchronous generator. We know the equivalent circuit of a generator, a voltage source in series with a reactance, or we can represent it by an impedance, EA, EB, and then we have and a neutral impedance Z N. Right, so this is the current flowing out, IA, ID and IC. So again we will be using the same method as we did in impedance loads. I will be going through this a bit quickly. So EA will be VAG will be equal to EA minus IA times ZY minus IN times ZN, and again when we simplify it and rearrange it, we can write it as EA minus ZY plus ZN IA minus ZNIB minus ZNIC. Similarly, VBG and VCG will also be found, can also be found. This would be EB minus IA times Zn minus Zn plus Zy IB minus Zn times IC, EC minus IAZN minus IBZN minus IC times Zn plus Z. Why? Next we will do what? We will convert them into matrix form. This will be of this form: Vp is equals EP, that is phase, minus Zp times I, right? And then we will use the sequence component formula. AVS equals AES minus Zp times AIS. What we have done, we have converted all the phase values into the sequence component values, and now let's pre-multiply with A inverse. A inverse AVS equals A inverse AES minus A inverse ZS AIS, right? A inverse times A, we already know, will be I, and I when multiplied by a matrix becomes the same. So this would be Vs is equals to Es minus Zs times of Is, where Zs, as we have already discussed in the load part, where Zs is equals to what? A inverse Zp A, and when we simplify it, it becomes what? Zy plus 3Zn 0 0 0 Zy 0 0 0 0, right? So now the sequence components will be V0, V1, V2 is equals E0, E1, E2 minus Zy plus 3Zn 0 0 Zy 0 0 0 Zy I1, I2 and I3, right? Now one more thing, when we are talking about the generator, the phase sequence is always positive. The direction of rotation will be reference, right? The angular separation is always same because it is fixed when the time of generator is designed. And if the magnetic field weakens, then all the phases, phase A, phase B and phase C, will be affected accordingly. This means if the magnitude of a generator rated at 11 kV gets low, then all the phases will have magnitude at 7 or 8 kV. Now this means what? That the voltage generated by internally generated voltage in a generator is always balanced, and when it is always balanced, this means what? The negative as well as zero sequence components will be zero, right? So now our equations will become V0 equals minus zy plus 3zn I. V1 equals E1 minus, sorry, this is I1, this is I1, this is I1 minus 2. I1 times Gy, and E2 equals minus I2 times C. So if we draw this network, let's start with V0. Zy plus 3zn, this means series. Zy 3zn plus minus V0. And since the current is negative, this means the current is not flowing inwards, rather it is flowing outwards. What about the positive sequence network? There is a source involved, E1. I1, Zy, and this will be V1, right? And what could be the negative sequence network? No source involved. Zy, which is equals to G2, of course. I2, G2. I am repeating again why I have taken these two as 0, because in case of a generator, the angular separation is kept very carefully at 120 degrees. The angular separation only gets disturbed when the generator is kept. In that case, the generator will not be affected. And even if the field weakens, all the three phases will be affected accordingly. This means that the generator internally generated voltage under all conditions is equals to what? The same, right? So is equals to the same, and that is why we say 0 and negative sequence are 0. 0 and negative sequence are 0. This is Z1, Z2. Practically these are not equal to same. Z1 is more and Z2 can be same, but Z0 is different, right? So why? Because their neutral impedance gets it. So this was a detailed analysis of sequence networks of generators, transformers, and loads. In the next video, we will be using these sequence networks for